factoring expressions with trig functions. So again, let's review this from algebra. When you want to factor something like this here in part A, the first step of factoring is always to pull out the GCF. In other words, you look at your two terms and you determine if they share any factors in common. And of course, this one shares a factor of 3 as far as the numbers go. 3 goes into both 12 and 3. And x's, they share a factor of x squared. The second term only has 2 x's, so that's the most that they have in common. Then I open a parentheses and I fill in what's remaining after pulling out the GCF. Looks like from the first term I have a 4. 3 times 4 would be 12. I have a single x left. I took 2 out. Plus, let's see, I took out the 3. Actually, I took out everybody. There has to be something left, though, when I multiply, and of course, that must be a 1. You can check this very easily, right? By distributing this back, you're just going to get back to what we originally had. Here, then, would be the final factored answer. Well, it's the same thing with trig. If we look at example A on this side, here are my terms. Terms are the pieces separated by the pluses and minuses. What do they have in common that I can factor out? Definitely the 3. Oh, and they each have a cosine x. From the first term, again, I took everybody, so leaving me with just that 1. And then in the second term, the only thing left would be tangent squared x. So we have successfully factored that expression. Now with trig, we know there's all these ways to simplify. When you see 1 plus tangent squared x, you're supposed to realize, wait, that's a Pythagorean identity. 1 plus tangent squared x is equal to secant squared x. And then I'm looking at this thinking cosine and secant are reciprocals. This must clean up somehow. What if I reciprocate the cosine down to the bottom? These are all pieces that are being multiplied, so this is a perfectly valid move. The cosine would reciprocate to the bottom as a secant, and then this secant would divide out one of the ones on the top, leaving me with a final answer of just 3 secant x. I think that's the simplest we can write it. Okay, what about example B? Well, on the algebra side, I'm looking at my two terms. They do not share any factors in common, so pulling out the GCF is not going to work. When you have two terms and you want to factor, the primary thing to look for is called a difference of squares. Is it a difference? In other words, is there a subtraction? Yes. And are these pieces perfect squares? And the answer here is yes. 4x squared is a perfect square because 2x times 2x makes 4x squared. 9 is a perfect square because 3 times 3 makes 9. In other words, each piece is something squared. Some people even like to write that down. This is 2x squared. This is 3 squared. Well, once you determine that, a difference of squares has a specific factoring pattern. The pattern always goes a plus b, a and b are the pieces being squared, and a minus b. A plus b, a minus b. Here would be the final answer to this factoring problem. Of course, you could FOIL it out to convince yourself that we did it correctly. Well, it's the same thing when trig is involved. I'm looking over here. 16 is certainly a perfect square. 4 times 4. I see the subtract. That's good. How about cosine to the 4th x? Well, isn't that a perfect square too? Any even exponent there would be a perfect square. 16 is 4 squared. What would I square to get cosine to the 4th x? Well, it would simply be cosine squared x. Cosine squared times cosine squared would be cosine to the 4th. There'd be 4 cosines in all. That means I can use the factoring pattern. It is a plus b. A and b are those pieces being squared, so 4 plus cosine squared x times 4 minus cosine squared x. If you FOIL that back, you'll get back to where we started. Am I finished? I am not finished. These difference of squares are notorious for continuing on. Notice I now have two binomials. This binomial has a plus. There is no factoring formula for the sum of squares, so I can't do anything with that. But look at the second one. It has a minus. That's a difference. 4, that's a perfect square. 2 times 2. Cosine squared x, that's a perfect square. Cosine x times cosine x. So that one keeps going. Again, I can't change the first one. But this can be factored now. A plus b, a minus b. A would be 2. 2 times 2 is 4. B would be cosine x, because if I square that, I get cosine squared x. And then a minus b. 2 minus cosine x. This whole thing then would be the final answer to the problem. I don't have any simplifications here. The cosine squared x kind of reminds me of the Pythagorean identity, but all I'd be able to do is switch it over to a sine squared x, and I don't see how that would be any simpler. So this is it. That's the final answer. And then let's look at one more. Looking at the algebra side, when you have 3 terms, you should still always check for a GCF. I don't have one here. 3 terms should make you think this was somebody's FOIL problem. Often when the numbers are small, you can figure it out with some trial and error. I mean, doesn't the first have to be x and x? That's the only way you're going to make this x squared. And then the numbers at the back, they must multiply to be 21. Well, there's not very many numbers that multiply to be 21. The ones that come to mind are 3 and 7. I guess the other choice would have been 1 and 21. But then the middle one is always the key to figuring it out, because the middle term is the one that comes from the oi in the FOIL, the outer and the inner. I need these two, the outer and the inner, to somehow connect and make a minus 4x. Well, I think I can see how to do that here. If I put a minus here, that would give me negative 7x for the outer, and then a plus here would be plus 3x for the inner. Negative 7x plus 3x is negative 4x. Positive 3 times negative 7 is negative 21. And so we've got it. We've figured it out. This is the factored version of that polynomial. It's exactly the same thing with the trig functions. It certainly looks a little different, which I think can throw people off. But do you see that this is basically the same as working with x squared plus 3x minus 40? It's just that instead of having an x, I have a sine x. I have sine x that's being squared, and then I have 3 times sine x. But the process for working this out is exactly the same. Again, at the front, what could it possibly be except sine x times sine x? That's going to make sine squared x. The back number is negative 40. I need 2 numbers at the ends here that are going to multiply together to give me a 40. And then I also know that the middle parts are going to combine to give me a 3 sine x. Well, let's see, what makes 40? 4 times 10, I can't make a 3 out of that. How about 8 and 5, though? 8 times 5 is 40. I can make a 3 out of that as long as I do a minus 5 sine x for the outer and a plus 8 sine x for the inner. There's my 3 sine x. 8 times negative 5 is negative 40, and so we've got it. I have no other way to simplify this, and so here would be the final answer. Thanks for watching.